Okay, so yesterday we just went over all those preliminary things. And we talked about those two parts of a number with the count and the name. One thing I want to mention briefly before we jump into the material today is I hear it all the time from students, I can't do math or I'm horrible at math. The human brain is actually wired to do math. There are a couple of conditions to that though. Everybody's brain is wired slightly differently. Today I'm going to show you some things with operations and how you can do them differently, and we'll talk about it a little bit more when we hit it. But like I said, everybody's brain is actually wired to do math. The difference between someone who's good at math and somebody who isn't good at math is if they've had the experiences in their life to develop that part of the brain to activate it, to make it work. For a lot of people, that happens between the ages of 3 and 10. Some things that happen, some things you do, activities you do, the toys you play with even make a difference as to how active that part of the brain is. As an adult, you can still activate that part of the brain, it just takes more effort. So the only difference between someone who is good at math and someone who is not good at math is time and effort. So everybody can get good at math. I mean, I'm not up here saying that because I'm a math teacher and I get paid to tell you you can do it. The brain science and the psychological research is there. Everybody can do math. It's just a matter of how much time and effort it's going to take you to get there. And it's a matter of finding the process that matches up with the way your brain works. And we'll talk about that a little bit today as we're going through here. I want to expand a bit on those processes we talked about yesterday. That idea of a count and a name and a number. And I want to look at how does that tie in with the calculations we do almost every day and the way those things happen. And the one concept that ties everything together, it's another one of those very simple concepts that's often misunderstood and undervalued, and that is the idea of place value. Just to review a little bit, if we start at the end of a number, what's the place value of that last digit? The ones. The next one, tens, and then hundreds. And those are actually, our only three place values. They're repeated over and over again. Ones, tens, and hundreds. Ones, tens, and hundreds. Oops. And it goes over and over again. Now this first group is the base group. The next group is what's called the thousands group. And then the millions, and then billions, and so on. When we name a place value, we name its place value and its group. So this is just the tens place. This, of course, is the 10,000s, the 10 millions, and so on. Now, I'm not going to insult you by going through how to pronounce numbers and stuff like that. But there are a couple of reasons why I show you the place values and go through them. A couple of important connections with them. The first one is with just the structure of a number itself. Like 376. Most of us are used to seeing numbers like that, but many don't realize that that is actually just an abbreviation. The full form of that number would look like this. 300s and 7 tens and 6 ones. Some of you may have written numbers out like that at one point, and they called it expanded form. And it really is, it's just the full form of a number. With the number written in that form, we can see that each digit of the number has a count and a name. This isn't just a 7, it's 7 tens. So it has a name attached to it as well. So when we look at our basic operations, that'll be important. The next reason why it's important to understand those place values is for problems like this. Round to the nearest 100. And let's say I give you the number 7,473. Well, most of us know how to do that, but let's look at what it actually means. When we're asked to round to the nearest 100, what that's asking you to do is to refer to a number line that is numbered in hundreds. 7,300, 7,400. Pretend these are evenly spaced, 7,500, 7,600, and so on. And we know that 7,473 is between 7,400 and 7,500. So we know it's in that range there. The 7,473 is somewhere in here. Physically, which one of those hundreds is it closest to? 7,500. So it is nearest to the 7,500. So when we're asked to round to the nearest whatever, that is technically what it's asking us to do. Now, we don't want to draw out a number line every time we round a number, so we were taught a shortcut. What most of us were taught to do, if we're rounding to the nearest 100, we identify the digit in the hundreds place. What digit in this number is in the hundreds place? The 4. So that's the hundreds place. And now we know that 4 is telling us that it's between the 7,400 and 7,500. Then we look at the next digit, and that next digit tells us which one we're closest to. 5 would be right in the middle. If that next digit is 1, 2, 3, or 4, that would tell us that it's closer to the one below, the 7,400. If it were 6, 7, 8, or 9, it would tell us it's closer to the next one up, the 7,500. So since that's a 7, it's telling us it's closer to the next one up, 7,500. What if that next digit were a 5? So let's say it's 7,458. Well, we find that hundreds digit, that's the 4 still. So we know it's still between 7,400 and 7,500. But that next digit is a 5. What do we do? Well, we don't actually have to look at the ones. Whenever that next digit's a 5, we've been told that we have to round up. All 5s we've been told round up. Most of us were told we do that just because that's what we do, right? We've accepted that. It's not totally true, because it's not just a 5 there, there's information after it. It's not halfway, it's at 58. So the reason we take those 5s and round them up is because there's usually digits that come after it that tell us we're past the halfway point. So it truly is closer to the next one up. Now, the only time it would ever really be an issue would be if it was like 7,450. There's nothing after the 5, so it is truly exactly halfway. Well, even then, where do we round it to? We see a 5, we round up. And that's one that we've been told is just a convention. We've just accepted that's what we do. In this class, anytime we round, that's how we will do it. If that next digit's a 5, we will round up no matter what. For those of you guys in automotive, you may run into, with some of the mechanical designers and mechanical engineers you might work with, there are processes out there where if that next digit's a 5, some of them round up, some of them round down. We're not going to look, I won't show you that because I don't want to confuse you, but just be aware that there are processes out there. It has to do with error analysis. For every time that next digit's a 1 and it rounds down, you'll lose a little bit, but that's balanced out by whenever you see a 9, you round up to balance out the errors. It has to do with balancing out those rounding errors. We're not going to get into that, though. Since you've got the number line up here, by the way, let's take a look at something like, remember doing these problems? You've got a 7 and 13, fill in the symbol in the blank between them. What would we put in there? Less than, exactly. Some people have a hard time remembering what the less than symbol looks like. Some of you may have been told, think of it as an alligator, and the alligator wants to eat the bigger number. Well, that works, what really where it comes from is this. You have a number line with 7 and 13, and it's asking you which side is the 7 on. Well, here's the 13. The 7 is on that side. That's actually referring to an arrowhead at the end of the number line. Okay, back to our information. Let's now take a look at addition and how all of this applies to the operation of addition. I'm only going to do a couple of examples of each operation. This is just a really quick review for all of you. But let's take something like 427 plus 342. Remember, these are just abbreviations. The full form of that number, 427, would be 4 hundreds and 2 tens and 7 ones. 342, that would be 3 hundreds and 4 tens and 2 ones. It's been stressed to us since we first started adding multiple digit numbers that you have to line up the columns, right? Well, the reason for that, as we mentioned, each digit here is a count and a name. This isn't just a 2, it's 2 tens. And when we add numbers, add and subtract actually, if you recall from yesterday, first of all, they must have the same name. Then second, we're going to always combine the counts, but when we add or subtract, we're going to keep the same name. So when we're adding here, these 2 tens can only combine with other tens. So lining up the columns is just making sure that we're only combining things that have the same name. So once those columns are lined up, we can go ahead and add down them. 4 and 3 make 7. Now we keep the same name, so that's still going to be hundreds. 2 and 4 make 6, and again, we keep that as tens. 7 and 2 is 9 ones. So 769 is our answer. Now, some of you may have been looking at that thinking I did something really strange. What did I do there that's different than what you normally do? Yeah, I started from the front. I went left to right. Normally, we would do right to left. Why do we normally add numbers going right to left? In case we need to carry. There you go. We might have 458 plus 269. We would normally start on the right and work our way back to the left because of this. What's 8 plus 9? 17. Now we can't have 2 digits in our answer in a place value, so we're going to leave the 7 and carry the 1 to the next place value. 1 and 5, 6 plus 6, 12. So the same issue. We're going to leave the 1's digit, the last digit there, the 2, and carry the 1 into the next place value. 1 and 4, 5 plus 2, 7. So we have 727. Now, believe it or not, this process of carrying is a relatively new process. What I'm about to show you here, you don't need to write down. But before carrying was popular, one of the methods that would be used to adding numbers like this would look like this. 4 plus 2 is 6. 5 plus 6 is 11, so 1, drop the 1. 8 plus 9 is 17, so 7, drop the 1. 6 and 1 is 7, 1 and 1 is 2, and 7. You get the same answer. It looks very different, but it'll get you the right answer every time. The reason I bring this up, I'm not trying to change the way you add numbers by any means, but it's like I mentioned earlier. It's been ingrained in us that there's only one right way to do math, and that's not true. There's actually several correct ways to do math. I could show you 4 or 5 other ways to add numbers that would work every time. I'm not going to do it because I don't want to confuse you. But just because the way you do it is different than what I've showed you doesn't mean it's wrong. And it's as I mentioned earlier, everybody's brain is wired to do math, but everybody sees things a little bit differently. To some people, this makes way more sense, but to others, this actually makes more sense. And so the trick is finding the way that your brain actually thinks and learning to do math in that way. I'll get off my soapbox now and get back to the class here. To be totally honest, when it comes to adding, multiple digit numbers like this, by the way, in here you will have one quiz. Your first quiz, you'll be asked to do without a calculator. Then after that, you'll be able to use a calculator on everything. But I do understand you guys do have calculators, and when possible, you will use them. So when you run into a problem like this, before you punch it in the calculator, I would expect that you would at least, think for a second. 458, well, that's about 500. 269, that's about 300. 5 plus 3 is 8, and that's going to stay hundreds. So I'm expecting an answer around 800. So when my calculator spits out 727, I know that it's at least a reasonable answer. The reason I stress that is because it happens to me all the time. I've got these fat sausage fingers, and when I'm punching buttons on a calculator, I might do 458 plus 269. Oh, 3,117. That must be my answer, right? What went wrong? I accidentally hit an extra key in there, didn't I? If I've done this little bit of an estimation here, I catch that, and I know 3,117 can't possibly be the right answer. If I didn't do that little estimation, I see it happen all the time. People write down that answer and continue on their way because the calculator is always right. I worked in engineering before I came here, and I saw it all the time. People would punch something in the calculator, and they would hit a wrong key like that, and they wouldn't catch it. And they would work for an hour and a half on a design based on a calculation that was wrong. And so they'd have to start all over. So it's important to have that estimate. The other thing that happens to me sometimes is this. 458 plus 269. Oh, the answer is 317. What went wrong there? Yeah, one of the keys didn't register when I pressed it. So again, it's not uncommon to press a key and it doesn't register. If you did that estimate, you catch it. If you didn't, well, you can sometimes continue on with that answer and not realize it. Doing that estimate doesn't catch every mistake, but it catches some of the really bad ones like that. Okay, let's look at subtraction. So let's take something like 738 minus 420, 21. I'm not going to write this out in its full form. I think you guys get the idea right now that you have to line up the columns when you add and subtract because you can only combine digits with the same place value. Once it's lined up, of course, we can subtract. 7 minus 4, 3, 3 minus 2, 1 and 8 minus 1, 7. What did I do again there that was a little unusual? Yeah, I went left to right again. Normally we go right to left. When we subtract, we go right to left in case we have to. Not carry, but when subtracting, it's called borrowing, taking away. There we go. We might have something like 826 minus 297. We go to subtract. We start on the right, working back to the left because 6 minus 7 can't be done. So what do? Borrow from the 2. That's a 1, and this is now 16. 16 minus 7, 9. Good. 1 minus 9, can't do it. So we have to borrow from the 8. This will be 7, and this will be 11. 11 minus 9, 2. 7 minus 2, 5. So 529. Once again, just like with addition, borrowing is a relatively new process. One of the ways this would have been done or could have been done before borrowing became popular might look like this. 8 minus 2 is 6. 2 minus 9 can't be done, so we're going to take from the 6. That'll be a 5. This is a 12. 12 minus 9 is 3. 6 minus 7 can't be done. We'll take from the 3. That's a 2. This is a 16. 16 minus 7 is 9. Notice we get the same answer. We're moving left to right instead of right to left. Again, I'm not trying to change how you subtract. I just want to show you that there are other ways of doing it. Again, I understand that the calculators are there and you're probably going to use them. If you're going to punch this in the calculator, this is close to 800. This is close to 300. 8 minus 3 is 5, and we keep the hundreds. I'm expecting an answer around 5. Any questions so far? All right. Let's look at multiplication. Now, with multiplication and division, if you recall from yesterday, we don't need the same name because we're going to combine the counts again, of course, but we're going to also combine the names. So let's take something like 32 times 21. And I am going to go ahead and write this out in full form. So 3 tens and 2 ones and 2 tens and 1 1. When we multiply, we do not need the same name. So what that means is these 3 tens here not only can combine with these 2 tens, but it can also combine with the 1 1. In fact, every digit in one number can combine with every digit in the other number. And that's really all that the process of long multiplication is an organized way of making sure that every digit in one number combines with every digit in the other number. Now, I showed you there's multiple ways to add and subtract. The biggest variations with multiplication is how you organize it. Depending on what region of the country you were taught math, or sometimes even if you're in a different country, they start in a different spot. In this region, we've been taught you start with the bottom number and the last digit. So the last digit on the bottom number is right there, the 1 1. And you use that to combine with every digit on the top number. And we work right to left to get at the last digit of that top number. So 1 1 times 2 ones. Again, we combine the counts. What's 1 times 2? 2, but we also combine the names. Ones times ones is ones. Then we move to the next digit in the top number. 1 1 times 3 tens. What's 1 times 3? 3 ones times tens is tens. Now we move over to the next digit. Before we can move over there, what have we been taught we have to do down here? Put in a 0, or again, sometimes you might just be taught to put in a blank, depending on where you were taught. So we put in a 0. The reason for that 0 will become apparent here. Now we move over to the 2 tens. We do 2 tens times 2 ones. Well, 2 times 2 is 4, but we also combine the names. Tens times ones is tens. We needed that 0 so that our place values would stay lined up. 2 tens times 3 tens. Again, we combine the counts. 2 times 3, 6, and we combine the names. Tens times tens, hundreds. And now we can combine. 2 and 0 is 2 ones. 3 and 4 is 7 tens, and 600. 672. So you can see that idea of a count in the name explains why we have to do things the way we do with our long multiplication. Now again, I do fully understand that you have a calculator. But before you punch that in, I would expect you to look at that and say, that's about 30. This is about 20. 3 times 2 is 6. Now when we multiply, we have to combine the names. 10s times 10s is hundreds. So I'm expecting an answer around 600. Does anybody know the shortcut for combining the names? You just combine the zeros. Okay? If I have something like 4,000 times 200, you do 4 times 2 is 8. I have 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. Thousands times hundreds is 100,000. Okay. Now a little bit of a note before we move on from our multiplication. We had memorized some multiplication facts that help us with that. But before we had memorized those, back in like first grade or so, when we had a problem like 5 times 3, before we had memorized our multiplication tables and knew that that had to be 15, how did we figure out what that was? There you go. 5 plus 5 plus 5, right? 3 5s added together is 15. Multiplication is defined as repeated addition. Now, with that said, let's move on to division. And we had said yesterday and today that division and multiplication follow the same rules, just one's going forward and the other's going in reverse. So if I have something like 24 divided by 8, if multiplication is repeated addition, division can be thought of as repeated subtraction. 24 divided by 8, I'm going to start subtracting 8 from 24. 24 minus 8 is 16. 16 minus 8 is 8. 8 minus 8 is 0. I subtracted it 1, 2, 3 times. 24 divided by 8 is 3 because we can subtract 8 3 times. In fact, that explains where our remainders come from. Like if we have 30 divided by 7. 30 minus 7 is 23. 23 minus 7, 16. 16 minus 7, 9. 9 minus 7, 2. And we can't subtract the 7 anymore. There's 2 left over. So 30 divided by 7, we subtracted 7 1, 2, 3, 4 times. So it's 4 with a remainder of 2. Now for right now, we'll leave it as 4 with a remainder of 2. And as we progress through the next few weeks, we'll see several other ways of expressing that remainder, like 4 2/7 or 4.28571429 approximately. Several other ways that we'll see of expressing that remainder. For right now, we'll just leave it as 4 with a remainder of 2. Now let's take a step up the level of difficulty a bit with our division here. What if we have something like 72 divided by 3? Well, if I start subtracting 3 from 72, this is going to take a while, isn't it? So to speed it along, let's subtract big bundles of 3. In fact, let's do bundles of 10. What is 10 times 3? 30. So let's subtract 30. That gives us 42. We've just subtracted 3 10 times. Subtract 30 again gives us 12. That's another 10. So we've done it 20 times now. Subtract 3 again is 9. That's 21 times. Subtract 3 again is 6. That's 22 times. Subtract 3 again is 3. That's 23 times. Subtract it once more is 0. That's 24 times. We just subtracted the 3 from the 72 24 times. 72 divided by 3 is 24. The process of long division is nothing more than a way of organizing what we just did right here. Subtracting that 3 or whatever number we're dividing by over and over again, but doing it in large bundles so we don't have to take forever to do it. For example, let's say I have 69,825 divided by 21. There is no way I'm going to start subtracting 21 from 69,000. We don't have that kind of free time. So I'm going to start trying to do it in big bundles. How do I know what size bundle to use? Well, I look at the place values of the number I'm dividing. I look at this first digit here. What's the place value of that 6? It's in the 10,000. Good. So we do 10,000 times 21. What's that give us? 210,000. Can I subtract that? No, it's too big. So I go to the next place value. What would the next place value be? 1,000. 1,000 times 21 is 21,000. Can I subtract that? Sure can. In fact, I can subtract it more than once. Shorten up just a little bit. How many times can I subtract that? 3. 21,000 times 3 is 63,000. So I subtract, I've got 5, 2, 8, 9 minus 3 is 6. What I just did there is I subtracted a bundle of 1,021. And I did it 3 times. 1,000 times 3 is 3,000. So what I did right here is I subtracted that 21 3,000 times. So that was the thousands. What's my next place value? Hundreds, right? 100 times 21 is 2,100. Can I subtract that from what's left? Sure can. More than once even. How many times? 3 again. So 2,100 times 3 is 6,300. I've got 5, 2, and 5. So again, I just subtracted a bundle of 121s and I did it 3 times. 100 times 3 is 300. I subtracted 300 more 21s. Next place value is 10. 10 times 21 is 210. I can subtract that. Looks like what, twice? 210 times 2 is 420. Leaving with 105. So again, that was a bundle of 10 and I did it twice. That's 20 more. And of course, all that's left is my ones. 1 times 21 is just 21. That'll go into here 5 times. It's 105, there's nothing left over. So I subtracted it 5 more times. So 69,825 divided by 21 is 3,325. Now you might be looking at what I just did and thinking, that looks absolutely nothing like how I was taught to do division. And it looks very different, but it's actually exactly the same process. What most of us were taught is just an extreme abbreviation of that. For example, do the same problem here. What we were taught, you got the 21, does 21 go into 6? No. So we leave it blank above the 6. That's exactly what we did right here. The 210,000 was too big to subtract, so we moved on to the next place value. So we move on. 69 now. Does 21 go into 69? Sure. How many times? 3. 3 times 21 is 63. We subtract to get 6. What we just did there is exactly what we did here. We just left off all the zeros. So now then, depending on where you learned, many of us were taught to just bring down the next digit. Some of us were taught to bring down all of the other digits. Either way, the next digit we got to deal with is that 8. 21 goes into 68 3 times, right? 3 times 21 is 63. We've got 5 left. Once again, that's exactly what we did right here. We just left off all the zeros. So you can see it's the same process. It's just been shortened and abbreviated to try to make it easier. I'm going to get back on my soapbox for just a second here. This is one of the reasons why people struggle with math, is rather than showing the long process like this, you understand why the steps happen the way they do. I mean, looking at this, it probably confused the heck out of you guys because you've never seen it before. But if you do that a few times and actually understand what's going on there, it explains there's a reason why each step has to happen the way it does. It explains why it has to happen. This one is so abbreviated, and we tend to have done that with math through the years. We abbreviate it to the point where it's just, you have to just memorize it and do the process. There's no real reason behind each of the steps anymore. Okay, with that, depending on which clock you believe, we have anywhere from 12 to 15 minutes left. So what I'm going to do is I'm going to give you the homework. Like I said, I always try to give you about 10 or 15 minutes to start on the homework. In your book, on pages 8 through 10, I want you to work on problems 1 through 69, the odd numbered problems. As I mentioned yesterday, there are 35 problems there. You don't necessarily have to do 35 problems with the homework. If you do the first couple and they seem pretty easy, feel free to skip ahead a few and do some of the more difficult ones. My main concern is that at the end of this assignment, you know how to do it and you're comfortable taking a quiz on it. Make sure, at the very least, you do a few of the word problems, because most of the assignments do have word problems at the end. Make sure you at least do the word problems. In just a second here, I am going to hand out an answer sheet. That answer sheet, there's the reason why I assigned the odd numbered problems. There's two reasons, actually. One is I don't want you to have to do 69 or 70 problems. Two is this answer sheet has the answers to the odd numbered problems on it. So as you're doing your homework, you can check your answers to make sure you're doing it right. I'd rather have you do 1 or 2 problems and check it and make sure you're doing it right than have you do 20 or 30 problems and find out tomorrow you did them all wrong. Doing them wrong doesn't do you any good. So I'm going to hand out that answer sheet in just 1 second. Any questions? Okay.